So you'll see it soon. Anticipated due date will be this Friday. Given that this Friday at this time slot, I expect to run a review for all of you who may be interested, to serve the purpose of getting ready to be successful on the final exam, which I believe is on Monday. It's in the syllabus. Location, I will let you know. And exam 3 will be scanned today. Results will be up this afternoon. Now, our last major consideration. Chapter 23. The stuff leading up to section 23.8 in chapter 23 is really aimed at serving the purpose of having you understand important trends, periodic trends in atomic size. But you should have been through this in 2045. In the main, size trend considerations apply to A family, not B family atoms, and show that as we go across a period, like lithium through neon, or sodium on down through argon, atoms get progressively smaller as you go left to right, but not substantially so. So for neighboring in-period A family atoms, we generally do not observe a significant difference in size. So neon smaller than fluorine atom, but not a whole lot. Fluorine smaller than oxygen atom, but not a whole lot. Of course, when you add up all these small differences, you recognize that lithium is a lot bigger than neon. And when you start to talk about this in 2045, I expect that you would find this unusual, since lithium atom is composed of 3 protons in the nucleus, 4 neutrons for the average lithium atom, and 3 electrons surrounding. But when you get to neon, you got 10 protons in the nucleus, average neon atom 10 neutrons in the nucleus, and of course 10 electrons surrounding. So here's an atom composed of a hell of a lot more particles, which is a good deal smaller than the atom composed of many fewer particles. Why is this? Well, you talked about effects, I trust, in 2045, which allow you to, shielding is one of them, electron penetration, which is related to shielding, and effective nuclear charge, which is really where all this is at, so to speak. As you go left to right across a period, effective nuclear charge increases substantially when you make the entire transition from the left-hand side atom, lithium, to the right-hand side atom, neon, for the second period of atoms. So that accounts for the trend. If you want more explanation, it's all in the notes, but I hold you not responsible for the explanation. But we do need to pay attention to the size trend itself. In family size trend, again, A family atoms. For the atoms within a family, as you go from period to period, in general, we observe a large increase in size. Point, sodium atom, in the same family as lithium atom, but in the third period, with lithium in period number 2, Sodium atom's a lot bigger. Correspondingly, potassium atom's a lot bigger than sodium atom. To jump to the right side atoms, discounting the noble gas atoms, because they don't really show us much chemistry, and make the atomic size comparison for the halogen atoms. Chlorine atom a lot bigger than fluorine atom. Bromine atom a lot bigger than chlorine atom. Iodine atom a lot bigger than bromine atom. So, regarding our concern, how to rationalize Bronsted-Lowry acid-base strengths. Because back in chapter 18, all we said, here's the acids and here's the indication of their strengths, the Ka values. Can we provide an explanation of why acids show the Ka values which they show? Why do they show the strengths which they show? Yes, we can. We do this by taking any atom under consideration and assessing the effective negative charge density of the conjugate base of the atom. Now be careful of this term negative charge density, because it doesn't mean that the species is negative. It doesn't mean that it's an anion. Water, for example, is a stronger base than chloride ion. And water is neutral. So in water solution, you have to realize the effective negative charge density of the neutral water molecule exceeds the effective negative charge density of the negative chloride ion. How do we know this is true? Well, if H plus is jumping into a solution containing chloride ion or the water molecule, on which of these two species does the H plus preferentially land? On water. Is an HCl a good deal stronger acid than hydronium ion? Because the bottom line in all of this, the facts. What are the facts? Because we have to cook up rationale, explanations which keep with the facts, which support the facts. And if we cook up explanations which fit the facts, then we have reason to believe that our explanations are sound, or at least usable. But if we cook up explanations which don't fit the facts, I don't care how good the explanations sound. These molecules don't change the way they behave. And if our explanations don't support the facts, then we have to throw away the explanations and invent better ones. That's the way it is. So, with the size consideration and the relationship of size consideration to effective negative charge density, ENCD for shorthand, of a conjugate base for an acid, we're starting on page 2330 in chapter 23. Because in order to get at this explanation, rationalization of strengths of Bronsted-Lowry acids and bases, we're going to assemble a number of considerations which are relevant to the problem. The first one we're going to consider is charge to size ratio, since we have just reminded ourselves about pertinent trends in atomic size for A family atoms. Periodic trends for A family atoms. And you will see that on occasion we will come up with two considerations which are relevant to the acid and its conjugate base. Two considerations which apply, or two or more considerations which apply, to trying to assess the effective negative charge density of the Bronsted base, the conjugate base of the acid in question. And we will discover that these two or more considerations may in fact fly in the face of each other. This is difficult for folks at this stage of the game, because so far you've only heard one-sided arguments. Science, unfortunately, isn't so simple. You've only heard arguments provided which support the fact or consideration at hand. Now we're going to look at arguments which fly in the face of each other. This argument says this base is stronger, whereas this argument says that base is stronger. Well, between two bases, One of them's got to be stronger than the other. This we know for sure. So which argument are we going to use? Do you have an argument which says the conjugate base of acid HX is the weaker base? Or the argument which says that the conjugate base of acid HY is the weaker base? Because if we're comparing the two bases, X minus and Y minus, one of them has to be weaker. One argument says X minus is the weaker, more stable base, which makes HX the stronger acid. The other argument says Y minus is the weaker, more stable base, which makes HY the stronger acid. Which argument will we use? The one which fits the facts. If in fact HX is a stronger acid than HY, the argument we have to use is the one which allows us to explain why X minus is the weaker, more stable base. But we're still laying all the cards on the table. We're looking at all the relevant factors. And we're going to select those relevant factors which support the facts. Now, in addition, the stabilization of negative charge density as a consequence of charge to size ratio. If no other factors apply except charge to size, this is a single minus anion. This is a single minus anion. That's what this signifies. Based on charge to size ratio, which of these is the weaker, more stable base? Based on charge to size ratio. The bigger one. Because charge to size ratio here is smaller, right? They're each minus 1, but this minus 1 charge is divided by a much larger area. Now, I use charge to size ratio as a function of charge to area, because the charge of a species is really on its surface, not buried within, although you can make some arguments which would deal with volume to some degree. But let's just take a look at this on the basis of area. Remember, this is a sphere, not a circle. Okay? The spherical monatomic anion, like chloride ion. Spherical monatomic anion, like fluoride ion. So we'll write down example Cl minus, F minus. Okay? Now, in addition to this, how about trends in electronegativity? Do you remember what electronegativity is? Electronegativity is really a measure of Z effective. So if you know what Z effective is, you know what electronegativity is. Electronegativity, practically speaking, is a measure of the ability of an atom in the bound state, unless it's a monatomic species. But in the main, electronegativity is a measure of the ability of a bound atom to attract toward itself and stabilize what? Stabilize what? Negative charge density. Ha-ha, that's what electronegativity does. A measure of the ability of a bound atom to attract toward itself and stabilize negative charge density. So, if I have another base over here, which is about the same size as this base, which we've tagged as fluoride ion. Let's say it's hydroxide ion. So this would really look like this. There's the H atom. But we know from electronegativity considerations that for the hydroxide ion, the minus charge rests on which component atom? H or O? O. And that's why I tell textbooks they flunk when they write OH minus. They flunk. Because that says to a student the damn negative charge is on the hydrogen atom. And that's wrong. So you know me, I change the way formulas are written. And then from time to time I look at evaluations that I received from students in the past, and they say, Horvath's crazy. He thinks he can rewrite chemistry. I'm just making an attempt to do something called communicate successfully. That's all. And when I see stuff in textbooks which doesn't fit the facts, I don't give a damn if every textbook in the world prints this on their very expensive pages. I'm not going to use that stuff. Because it ain't right. And anytime those authors want to go to chemistry court and fight with me, I'm ready. They won't do it, because I'll beat the living hell out of them and they know it. Because I'll defend myself based on, guess what? Facts! Okay? So I'm picking on this as hydroxide ion because based on size trends, we know this is not going to be, it's going to be bigger than this, but not a whole lot bigger. Remember, because oxygen and fluorine are neighboring atoms. Oxygen atom's a little bit bigger than fluorine. So F minus, a little bit smaller than an oxygen atom with a charge of -1 on it, which is what it is in the hydroxide ion. Okay? Now then, let me redraw this. Redraw this so I can exaggerate. Here, big difference in size, chloride ion versus fluoride ion. Here, not much difference in size, just a little bit bigger. So I ask this question. If the difference in base strength of fluoride ion and hydroxide ion, if the difference in base strength between fluoride ion and hydroxide ion rested on charge to size ratio, which one of these would be the weaker base? Think before you answer. If the difference in base strength between hydroxide ion and fluoride ion depended on charge to size ratio, which would be the weaker, more stable base? Hydroxide ion. Now let's look at the facts. Which acid is stronger, HF or water? We know this. If nothing else, the information's in our acid-base table. Which is the good deal more strong acid, stronger acid? HF. So this charge to size ratio, which says this is the weaker and more stable base, is not an acceptable argument for these two bases, is it? Yet it applies, because all atoms, all ions have sizes. And all ions have charges. Now tell me, how do these two atoms, fluorine and oxygen, differ in electronegativity? It's a lot of fun to think about electronegativity. We told you that before. A lot of fun. Fluorine is number 1, the most electronegative atom. Oxygen is number 2. Nitrogen is number 3. And likely you recall, as you go right to left for neighboring atoms across period 2, you observe an EN difference of 0.5. So fluorine 4.0, oxygen 3.5, nitrogen 3.0, and you can keep on going. And along with that, we said the only other atom whose electronegativity is worth remembering is that of hydrogen, because hydrogen is the most common component of material. Most common atomic component of molecules. You remember the electronegativity of hydrogen? 2.1. There's only one nonmetal atom that has a lower electronegativity than hydrogen. We asked you this before. What is that atom? Boron, 2.0. But boron isn't going to be really much part of this consideration other than for the fact that it's the only nonmetal atom of lower electronegativity than hydrogen, because we don't find hardly any important molecules with boron in their composition compared to those with fluorine, particularly those with oxygen, particularly those with nitrogen, and indeed those with hydrogen. Here's the EN trend. Start with cesium at the lower left corner, discounting francium because of its very radioactive character. ENs increase along this diagonal arrow. That means ENs increase this way and ENs increase this way. This way in the family, this way across the period. And ENs have to increase this way across the period, since we've already stated that EN is really determined by Z effective, and Z effective increases this way. That's why atoms get progressively smaller as we go this way, even though they increase in particle count. All right? So with this information, you can now explain why, for this series of in-family acids, HF is the weakest because fluoride ion is the strongest conjugate base, and HI is the strongest because I- is the weakest conjugate base of the conjugate bases derived from these four acids. If you drew size pictures, you'd have something like this. I minus Cl minus B, pardon me, I minus Br minus Cl minus F minus. Charge to size ratio is increasing substantially as you go from atom to atom. Now it's true that the electronegativity of fluorine is a lot greater than that of chlorine. But chlorine, bromine, and iodine have very similar electronegativities. Chlorine 3.0, bromine 2.8, iodine 2.5, 2.6, depending on which table you look at. So, take note that if we attempted to decide how these acids, the halogen acids, should compare strength-wise, if we attempted to decide how these four halogen acids compare strength-wise on the basis of atomic electronegativity, we would argue that I minus, Br minus, Cl minus, F minus. Which of these four bases, based on electronegativity, should be the weakest, most stable base? Which one is derived from the atom of greatest electronegativity? Fluoride ion, isn't it? And electronegativity is a measure of the ability of the atom to stabilize negative charge density. Well, the more stable negative charge density is, the less reactive is the base. Hey. So based on electronegativity, we would argue that the conjugate bases derived from the four halogen acids would compare strength-wise. I minus strongest, F minus weakest. Does that fit the facts? No. That doesn't fit the facts. Because we know for a fact of these four halogen acids, I minus is weakest and F minus is strongest. So the electronegativity based argument is no good. So which argument are we going to use? Charge to size or electronegativity? Which one? Which one fits the facts? Charge to size. We talked about it over there. Chloride ion. A much weaker base than fluoride ion. We know HCl is a strong acid, HF is a weak acid. So this has got to be a much weaker base than this. But based on electronegativity, we're going to argue this is the more stable, weaker base. That doesn't fit the facts. So let's look at charge to size ratio. Because here you've got -1 smeared on this big atom versus -1 smeared on a much smaller atom. So here, negative charge concentration assessed by charge to size ratio. Here, negative charge concentration is greater. That makes this the stronger base. Does that keep with the facts? Is this a stronger base than this? Is this a stronger base than this? Yes, that's the argument we use. Now let's look at these two. Because based on electronegativity, I'm going to pick this as the weaker, more stable base. But based on charge to size ratio, this is larger, I pick this as the weaker, more stable base. Which is the more stable base? F minus. So which argument do I use? Electronegativity. Good. So there's our first example of two arguments, each of which apply to the case, but fly in the face of each other. Because for these two, the charge to size ratio argument says this is the more stable base. But that's not true. The EN argument, however, says this is the more stable base, because this is derived from the more electronegative atom. So we'll take that argument. Aha, but when I play with these two, then the electronegativity argument falls apart. Because the electronegativity argument for these two says this is the more stable base. That's not true. So I'll pick the charge to size argument. And I'm not surprised, because here the size differential is great, whereas here the size differential is not great. So when the size differential is not great, does that sound like that's where you better pay attention to electronegativity? And when the size differential is great, then it's likely size differential is what matters. When the size differential is great. So with that we can see why the acid strength trend for the halogen acids, it's HI strongest, HF weakest. But when we go to this in-period related gathering of acids, HF, water, we're starting at fluorine in period 2 and going right to left. Ammonia? Hell, we haven't even found ammonia to behave as a Bronsted acid, based on our considerations. And then methane. Well, since we know from knowledge of periodic trends that HF is a stronger acid than water, we've already established a trend, haven't we? If HF is a stronger acid than water, which is true, we can well expect water to be a stronger acid than ammonia, which is true, and we can well expect ammonia to be a stronger acid than CH4, methane, which is true. Now, doesn't mean methane and ammonia are strong acids by any stretch. Remember, we're making comparisons. That's all. We made the comparison successfully. Here is the acid strength trend for these in-period related acids. This is in family. And we reminded ourselves earlier, size trends, A-family atoms. As you go and compare sizes of atoms that share the property of being in the same family, as you go from period to period, you generally observe a big increase in size. But here, fluorine, oxygen, nitrogen, carbon, for neighboring atoms, there's not a whole lot of difference in size. Fluorine smaller, but not a whole lot smaller than oxygen. Oxygen smaller, but not a whole lot smaller than nitrogen. Nitrogen smaller, but not a whole lot smaller than carbon. So if I look at the difference in size between I minus and F minus, woo! Here's I minus, here's F minus. But if I look at the difference in size between F minus and H3C minus, I'm not going to see a whole lot of difference in size like I'm going to see here. But I'm going to see a hell of a big difference in electronegativity. And which argument supports explanation of this trend in acid strength? It's this one, isn't it? Not this one. Good. So on we go. We got two considerations thrown into our bag of factors that we have to pay attention to. Assessment of an effective negative charge density based on charge to size ratio. Assessment of effective negative charge density based on electronegativity. Now let's add to this collection of considerations. Considerations being these things that we have to think about when we're trying to make or offer an explanation on acid strength. Look at the acid. What's its conjugate base? How can I assess the effective negative charge density of this conjugate base? Well, I'll try charge to size ratio. I'll try electronegativity. And now I'm going to add induction. What does it mean to induce something? You heard about induction in physics class, I believe, if you've been in physics class. What does this word mean? Induction. Lewis structures. Trifluoroacetic acid. I am sure the name doesn't surprise you. Trifluoro, because we took this methyl group, which is present in the acetic acid molecule, and did some chemistry on these hydrogen atoms so as to replace them with fluorine atoms, to convert acetic acid to trifluoroacetic acid. However, you know, at least I hope you remember, we did this way back in chapter 18. When acetic acid does its acid thing, even though in one acetic acid molecule you got 4 hydrogen atoms, how many of these H atoms are ever losable as H plus from the acetic acid molecule? Just one. Which one? This one. This one only, because this leaves behind a minus charge on oxygen. Here, if I lost H as H plus, I'd leave a minus charge on carbon. How does the reactivity of carbon with a minus charge compare to the reactivity of oxygen with a minus charge? Which is by far the more reactive species? Carbon with the minus charge or oxygen with the minus charge? Carbon with the minus charge. Why? Why? Carbon hasn't got a sufficient electronegativity to stabilize negative charge density. But oxygen does. A lot of fun to think about electronegativity, isn't it? Now for trifluoroacetic acid, clearly there's only one losable hydrogen atom as H plus, because it's only got one. All right? So here are the conjugate bases derived from these two acids. Do they look structurally identical? Are they structurally identical? Yes, they are. Structurally and geometrically identical. But there is a difference in composition. But there's no difference in structure, no difference in geometry. And after each of these acids has done their acid thing, we wind up creating a minus charge on an oxygen atom, which is covalently connected to carbon, which in turn is connected to an oxygen by a double bond. Or is it a double bond after we did this? More on that later. And then covalently connected to another carbon atom. Except that this other carbon atom, for acetic acid, or in this case acetate ion, is covalently connected to 3 hydrogen atoms, whereas this one is covalently connected to 3 fluorine atoms. Question: if after I create these two anions, from the two acids respectively, trifluoroacetic acid and acetic acid itself. If the minus charge stays here, if that minus charge is not affected by any other component atoms or electronic properties of the species, if the minus charge just stays there, a minus charge on oxygen, an oxygen covalently connected to carbon, if that minus charge just stays there and is not affected by any other electronic or compositional features of these species, how will these two bases compare strength-wise? If the minus charge just stays there on the oxygen, how would these two bases compare strength-wise? How would they compare strength-wise? A minus charge on oxygen versus a minus charge on oxygen. How are they going to compare strength-wise? They'll be the same. And trifluoroacetic acid and acetic acid molecule would have the same Ka values. They'd be the same strength. Do they have the same strength? Hell no. One is a good deal stronger than the other. Which one is the stronger acid by far? Do you know? I'm going to either put an arrow this way, because this is the stronger acid, or I'm going to put an arrow, back arrow. Which is the stronger acid? Well, before we answer that question, let's talk about induction. How does the electronegativity of fluorine compare to hydrogen? A hell of a lot more electronegative those fluorine atoms are, aren't they? So if these fluorine atoms, by induction, can exert an electronic effect to the covalent bond skeleton, which is just a collection of electrons, valence electrons. If these fluorine atoms, because of their great electronegativity, can exert an effect through this covalent bond skeleton to pull this negative charge toward themselves, because they're number one in electronegativity, what will that do to this minus charge? Will it concentrate it, or will it smear it? Will it dilute it? If I smear this minus charge over the entire electronic skeleton of this thing because of these fluorine atoms, high electronegativity, what am I doing to the negative charge concentration on this species? Am I increasing it, not affecting it, or reducing it? I'm reducing it. I'm diluting the negative charge. What impact does that have on base strength? Weaker. Base strength gets weaker or stronger? Weaker. Ha ha! But how about these hydrogen atoms? You think they can inductively induce this negative charge to travel toward them? Hell, they're not even as electronegative as carbon. So these aren't going to do anything inductively. These aren't going to draw this negative charge toward themselves at all. So for this species, the minus charge remains much more concentrated on oxygen than it does here. But here, these electron hogs, fluorine atoms, draw this negative charge toward themselves through the electron skeleton, covalent bond electron skeleton of this species, and inductively stabilize this negative charge. So which is the stronger acid by far? Which one is the stronger acid between these two? Which one? Which of these is the weaker base? Which is the weaker base? This is the weaker base. So which is the stronger acid? This is the stronger acid. There's our arrow showing you, or caret showing you who's stronger. Induction. So in a nutshell, induction is an electronegativity effect that is exerted to the covalent bond skeleton of a species. How about that? We're only letting the facts talk to us. It has to be true. If we go to the laboratory and find this base is a lot more stable than this base, this acid is a lot more strong, is a lot stronger than this acid, which is true, then it must be true, this induction business. How about that? So, there's trichloroacetic acid. Compared to acetic acid itself and trifluoroacetic acid, tell me how the strength of trichloroacetic acid compares. Stronger than acetic, but weaker than trifluoroacetic. How about that? Oh, because chlorine is a good deal more electronegative than hydrogen, but not nearly as electronegative as fluorine. So chlorine, like fluorine, exerts stabilization of negative charge by induction on the negative charge created when trichloroacetic acid loses its H as H+, but not nearly as effectively as that of the fluorine atoms in trifluoroacetic acid. Now let's add one more consideration to this. 4. Induction and length of covalent bond skeleton. All right? Here's trichloroacetic acid. This is trichloropropionic acid. If I cared about the name, I'd write it down. I don't give a damn about the name. Let's just look at the structure. The only difference, well, it's a big difference, between this molecule and this molecule, they each have a carboxylic acid function. You'll learn about this nomenclature in organic. They each have this part in common, structurally and compositionally. They each have this part in common. A left side carbon atom with 3 chlorine atoms attached, a trichloromethyl group. But this has a CH2 group in between. Okay? Now then, each does its acid thing. We've already recognized that these chlorine atoms stabilize negative charge by induction. Question. If these chlorine atoms for this acid, the hell with its name, if these chlorine atoms stabilize that negative charge by induction as effectively as those, okay, then I'm going to smear this minus charge over a longer bond skeleton. Because this is a longer bond skeleton. I got a CH2 group in here. I don't have that over there. So I repeat, if these chlorine atoms stabilize negative charge by induction for this species as effectively as these chlorine atoms, which of these is the weaker base? The larger one? Absolutely. But now let's look at the facts. This base is much more stable than this base. When I put the H plus back, I find that trichloroacetic acid is a much stronger acid than trichloropropionic acid. So now what have I realized about induction? The atoms, which can stabilize negative charge by induction, have got to be fairly close to that spot or place in the species where the negative charge has been developed. Here, the chlorine atoms are another atom removed. And so, if we go to the laboratory and find the facts that that acid is a lot stronger than this acid, we now know that induction and length of covalent bond skeleton relate to each other. How? The ability for atoms of appreciable electronegativity to stabilize negative charge by induction. Can't do it if they're far removed from the site of negative charge development. If the covalent bond skeleton is long, induction effect is not much. But if the covalent bond skeleton is short, then the induction effect is appreciable. You see the relationship? You're going to pick it up from this point in tomorrow's last discussion class. Be there.